Today, we dive into a fascinating engineering challenge, which is controlling the inverted pendulum system using the stepper motor. It is a great way to understand how control systems work in the real world. It is like balancing a stick on your hand, but we will use motors, sensors, and programming to do all the heavy lifting here. The inverted pendulum, it's a great project because it combines physics, electronics, programming, and control systems into one complete system. And when all these parts work seamlessly together, it is quite satisfying to watch it. But before we get to the fun part, controlling the inverted pendulum, we have to cover the basics. So in this video, we will only focus on the stepper motor, how we can drive the stepper motor using the STM32 microcontroller. After, we will cover the encoder, and finally, we will implement control system algorithms to keep the inverted pendulum upward. So let's get started. Before starting, I also want to present the educational kit I'm using thoroughly. So this kit is from ST Microelectronics. So it has a rotary encoder where the inverted pendulum is attached. Then we have the stepper motor, and also we have this frame along with the stepper motor driver and the STM32F401 microcontroller board. So you have everything inside, so when you get it, you just need to assemble it. So finally, let's dive into the stepper motors. So the first thing is that there are plenty of materials and videos explaining the working principle of the stepper motors, so I'm not going to spend time on it. Instead, we will mostly focus on how we can drive the stepper motors. But of course, we will cover some basics to provide you with some context. So this illustration shows the internal structure of the stepper motor. So the rotor contains many teeth. So by magnetizing these coils, we can move this rotor by steps. So for example, if the rotor contains 200 steps, we end up with divided by 200, we have 1.8 degree resolution. So meaning that we can achieve a quite high position resolution. That's why stepper motors are mostly used in applications where high precision is required, for example, in 3D printers. Also, another feature is that nowadays you can divide one step into micro steps. So for example, if we can divide one step into 16 micro steps, we end up with even higher resolution, 0.1 degree. So next thing, let's talk how we can drive the stepper motor. So when we drive the stepper motor, of course, we cannot directly connect the stepper motor to the microcontroller because of the power limitation. So instead, we have motor drivers. So we have motor drivers as the bridge between the microcontroller and the stepper motor. So in this educational kit, we have the following motor driver expansion board, which you need to fit on top of the microcontroller board. So this expansion board is based on this stepper motor driver. So it provides everything to drive the stepper motor. So for these connectors, you need to connect the stepper motor, and also we have these pins to connect the power supply. So if you go to this manual, it explains how you can connect the stepper motor to to the motor driver. So next thing, we need to develop code to drive the stepper motor using this driver. So next thing, I'm going to show the header file and the source file for this stepper motor driver. So to develop the code, of course, we have to extensively work with the datasheet of the motor driver. So here is the um, motor driver datasheet. So let me scroll down, and here we have this schematic which shows how we can work with the motor driver. So here we have pins to connect the motor, we have a power supply, and then we have these pins to control the motor driver. So first thing, as you see, we have these these pins, clock, data out, data in, chip select. So as you get, we have, as you understand, we have SPI interface to control the stepper motor. And also we have these pins, additional pins to control it. So this flag pin is basically necessary to so if something goes wrong with the stepper motor, like if we are providing too much current, for example, if we have thermal shutdown, this pin goes down. So by reading this input pin, we can understand the status of the stepper motor. This is it's not so important for us. This is necessary just to reset the motor driver. And then we have this pin, which is quite important. So as I said, stepper motor rotates with steps, but the question is how we can control the frequency, how fast this rotation happens. So for example, so in our case, for this pin, we need to provide a square shape signal. So in every period, we will end up with one step movement. So in our case, if we have, let's say, 200 steps, and if we provide a square shape signal, or let's say PWM signal with 200 hertz, the stepper motor will do 200 steps per second, meaning that it will do one rotation per second. So by controlling the frequency of the PWM signal for this pin, we can control the speed, the speed of rotation of the stepper motor. And then we have this pin, which is necessary to control the direction of movement, direction of rotation. So it could be clockwise or counterclockwise. So these two pins are quite important to control the stepper motor. So next thing, let me show my project. So first, let me open the IOC file. So we have this F401 microcontroller, and as I said, we need a SPI interface. So if I open connectivity, we have SPI1, and we have the following pins, PA5, 6, 7. And if I open parameter settings, there's nothing new, I would say. I just set the scalar to 32 to have at most 5 megahertz SPI frequency. And also we need a chip select pin, so I am using PB6 for that. So here I configured it as GPIO output. Another thing, as I said, we need a pin to provide the PWM signal and the direction pin. So let me open the configuration again. So we have PC7. So I configured it as timer 3 channel 2. So if I open timer 3, channel 2 is to generate a PWM signal. Then we have a direction pin, and also we can reset, and also we have this GPIO input to read the flag of the stepper motor. That's it from the IOC file. Clock configuration we set to 80 megahertz. Almost we reached almost the maximum frequency. So that's it. So you just need to save the file to generate the code. And before moving further, I want to mention that all the code I developed is available on GitHub Steppeschool organization. So it has a repository for this project, and we have other projects as well. And you can get access to all these materials by becoming VIP member on my Patreon. So you can find the link in the description below. So if we move further, I created a header file and source file for this stepper motor driver. So so the first thing we have these macros. So we have a maximum acceleration, maximum speed, but right now in the current version, I don't have I'm not using these macros, so these values are just random. So that's why I set this question mark, but later we can set real maximum acceleration and the maximum speed we can achieve. Then we have a maximum current and current reference. So this I get from the stepper motor we are using. So we have the following stepper motor with 200 steps. But as you see, we have 3200 instead of 200. Why? Because as I said, we can use micro stepping. So if I search for micro stepping, in this stepper motor, we can achieve 16 micro steps per step. So eventually we have 200 multiplied by 16. So the stepper motor will do 3200 micro steps per revolution, per one rotation. So that's why I have this value. And I also defined another floating point value to define a 2 pi value. Then we have these macros for registers of the motor driver. So if I open it here, so here we have the table, and from this, using this table, I defined all these macros. And another thing is that for this motor driver, stepper motor driver, we can send a particular commands to control the stepper motor. So if we just send this value, we can enable the stepper motor. If we send this, we can disable it, and also we can read the status of the stepper motor. Then we have the timer frequency. And also we will work with position, angular speed, angular position, angular acceleration. We have other things. So to encapsulate all these pieces of information, I created an struct. And also I have another struct for the motor driver. So here we have the SPI interface. Also, we have a timer handler and a timer channel for generating a PWM signal. Then we have other members for direction, reset, and chip select pins. Then we have prototypes of the functions. So next, let me show these functions. So if we start from simplest, from the basic functions, one thing to note is that in this stepper motor, we have a thing called daisy chain. So usually when you have an SPI interface, you have separate chip select pins for each device. But when you have this daisy chain configuration, you can use just the one single chip select line to communicate with multiple devices. So how it works, like when you send the 1 byte, you need to set and reset the chip select line. So this device 1 will send the data sent to the next device. So if you want to send this data to the next, you do this resetting and setting again. So by doing this operation feature, you can use just a one single line instead of multiple chip select lines. So that's why every time when I receive or transmit through SPI, I have to reset and set the chip select line. Next, let me show the initialization function. So here I just reset the driver using the reset pin. Then I set the current reference. So in our case, we have 350 milliamps as the current reference. So if you look here, I have something quite similar. And also I set maximum current to half 500 milliamps. So that's how I initialize the stepper motor. There could be additional steps, but we will add it as we progress in our project. Then we have this function to set the frequency of the input PWM signal. So we have this step. So we have this auto reload value to set the frequency of the PWM signal. So what you have to do, you have to divide timer frequency, which is 1 megahertz. You need to divide by the frequency you want to achieve. So we have to set this value, and then we have to set the capture compare value to the half of the auto reload value. So and then how I achieved 1 megahertz. If I open IOC file again, if we go to timer 3 configuration, I set the prescaler to 79 to have 1 megahertz frequency. And if you're not aware how to work with this auto reload prescaler, I have a separate video on my channel to explain all these parameters of the timer. So next we have this function to set the velocity in radians per second. So if I set to 6.29, for example, which is equivalent to 2 pi, I will do 1 rotation per second. But if I set, for example, 62.8, can you guess what will be the step? The speed, it will be 10 revolution per second. So this velocity is in radians per second. So here I check if the velocity is greater than 0, I have to set the direction pin. If it is less than 0, I have to reset the direction pin. Then I update the stepper motor velocity, and then I do this scaling to set a proper frequency of the PWM signal to achieve this velocity. And also we have these functions to enable and disable the stepper motor. We just need to send the corresponding data to the stepper motor. And next thing, we are going to test the stepper motor. So let me open the main.c. So here we have the struct to define. So here we define all the parameters we have. So we have chip select, direction, and reset pins. We have the SPI. We will use SPI1, and for generating PWM signal, we're using timer 3, channel 2. Then we have we initialize, we enable the stepper motor. Then after some time, we set the velocity, which is equal to 6.28. So this will provide 1 rotation per second. Or 60 RPM. And also I forgot to mention that we have another function to read the position of the stepper motor. So for that, we have to read this register of the stepper motor. It contains 3 bytes. Then we have to do some shifting to get the absolute position. Then I take the remainder from the steps per revolution to get the angular position. Then I have to do some manipulation to get the position in radians. So that's it. Next thing, we are going to test how all these things work. For that purpose, I'm going to debug the microcontroller. So to test the stepper motor, I removed the inverted pendulum and the encoder, and I touched this red flag. So we can clearly see how the stepper motor rotates. And also another modification is that I created this global variable to um, to read the position of the stepper motor. Also, we can plot it using the serial wire viewer. So if you don't know how to do this, also there's another video on my channel to do this serial wire viewer configuration to plot the global variables. So we have everything. So when I press this float speed should change according to the velocity we set, which is 1 rotation per second. So let me resume the code. And as you see, the stepper motor started rotating. And we can look at the values. So in every 1 second, we have one period. So we are getting the correct values from reading the stepper motor absolute position register. So everything is working. So next thing, we will switch to the encoder, find the control system algorithms to control the inverted pendulum. And if you're interested in other parts, please subscribe so you don't miss new videos. And also, if you have any questions or remarks, don't hesitate to leave a comment in the on this video. And also, I want to mention my website where you can find courses on STM32 programming and designing a balancing robot, and also about the attitude estimation using the IMU sensors. These courses are a great material uh, to boost your knowledge and skills in programming in robotics. That's it for today, and see you soon.